the tree abstract data type. Okay, we can imagine creating a tree object with a predefined interface if we wanted to, right? We could say, okay, well, we're going to need to create a tree. What are some of the methods that we could imagine creating for this tree abstract data type? The textbook does go over the tree abstract data type in a lot more detail than we are going to, but I think it's worthwhile to think about this a little bit. What are some things that we might want to know about our tree if we were creating a whole object that is an arbitrary tree? How many leaves? Okay, that's not a bad idea. That's not a bad question. What else? When you say node, what do you mean? Because you're not wrong. You're very much on the right track. But when you say node, why are you saying node? Okay, but now we've got the idea of an element in a tree. And the node idea is also a good concept. So we might have things like this, right? We might want to get the root, right? The root's important. Hey, what's the root of this tree? We might want to know what the length is, aka the number of elements within the tree, the number of nodes within the tree. That's kind of a weird concept because it's hierarchical. Length is not a great term there, and you can already start to see the problem with using this sort of approach to a tree. We could see if it's empty. That's not a bad idea. Hey, does this thing have anything in it? We could pass the tree a node and ask whether it's either a leaf node or the root node. Those are valid ideas. Or we could say, hey, does this tree contain this element in one of the nodes? Here's an element. Does this exist anywhere in the tree? These are really good elemental behaviors that really we could do with anything, with any tree implementation. Other behaviors are going to require some sort of ordering to our tree, and we're going to talk about those different ordering methodologies. I say this to say that there's nothing wrong with having these orderings, but you do have to make some decisions at that point. What order are we going to visit the nodes in? What do we consider a node before another node? What about after, right? These are decisions that you're going to have to make. And it's not a bad thing that you have to make the decisions, but now all of a sudden, hey, what's the next node after this node becomes a question of traversal, which we will talk about in much more depth later on. But we've said the word node so often. Now we need to talk about what it is, okay? I know this is going to be unsurprising to you, but it is similar to a node in a linked list, okay? And it contains data. It contains the elements of the tree. This is the thing that contains our actual information. What else does a node in a tree contain? Okay, so we have next node, and by next node, I presume we mean child nodes, and the parent node, if there is one. So, just like our linked list, right? So, we need to create a node that does this, right? And we're going to create a generic one. So let's do this. Let's create a generic node, okay? And we'll call it generic tree node. Why are we calling it generic tree node? Why are we calling it generic? What makes it generic? Okay, that's a good idea. It's not a root or a leaf, but that's not, remember, a root node is just a node without a parent, and a leaf node is just a node with no children. What other kind of trees are we going to talk about later on? Right? Or put another way, how many children can a generic tree node have? Yeah, okay. So binary tree can only have 2 children. Is that a requirement for a tree? Or could a generic tree have more? Right, right. So no, we could have way more. We could have truly an indefinite number of children. And in some tree structures, this is true. If you look at the organizational chart for Harrisburg University, um, almost everybody reports to Dr. Mattis, the provost. So every faculty member and many staff members, right, report to the provost. Well, between full and part-time faculty, there are over 600 faculty members alone. So our organizational chart looks like this, right? And that doesn't even count things like student services. So that's the kind of node that we're looking to create here. So what information could we pass in to the constructor? Okay, remember, we're not creating the tree, we're creating the nodes, right? We need to create the nodes, and the nodes form the tree, just like the nodes form a linked list. So root right now holds no meaning. Okay, so right, we're going to have to take the element, so our data, and like our linked list, we're going to say that's nullable. What else? What other information should we be capturing? Okay, good. Child nodes, so we'll call it children. Does a node require children? Okay. What else? What else could we have? Yeah. Right. And we can go in and we can do our normal stuff. Right? Right? Self.data equals data, self._parent equals parent. Hey, what do we want to do with children though? What do we want to store our child nodes within? Considering that we could have between 0 and an almost infinite amount. What kind of storage paradigm should we consider for our child nodes? A list. A list would be great. Okay. So we're going to do this, right? If children is none, we are going to go self._children equals an empty list, right? Because we don't have anything there. Else, we're going to do this. Crap. Anyone know why we didn't just do that? Anyone have any experience with this? So if we do this, let's leave that there, and we'll come back to it. So we can do some fun methods, right? We can do our getters, get data, right? Return self dot. Uh-oh. I hear a baby. Get parent. Get children. And we can do our setters. Although, what's going to be interesting about children? What are we going to have to do differently if we want to do a setter with children? Well, yeah, we might have to do maybe not set because it's not one thing, right? It has to be chosen from a list, so the net result's not going to be set as much as add or remove, right? So we'll do that, and we'll say self.children.append, right? New child, and we'll do remove child, and we'll go this is a little inelegant, I will tell you that. And if we had a little more time and I wanted to spend more time on this, I probably would do something like this. Not just this direct, but also one where you would give a node and it would find it, or give an element and you would find it. But yeah, something like this would work, right? Now, here's going to be the issue with what we did up there at the top. Node 1 equals node node 1 dot add child equals node, and we'll give it we'll give this root, and we'll give this child. Okay, and we can go node 1 dot get children 0, and we can print that. And what will that print? And this will print child. And this will print nothing, or it should print nothing. Oh, what did I miss? Ah, that's what I missed. That's square brackets. What am I missing? No attribute get children. Oh. Let's try that again. Do you guys see what I'm doing wrong here? Oh, I see what I'm doing wrong. I'm doing what you guys do sometimes. Everything's embedded inside the initializer. Right? So that I want to re-embed. Okay. There we go. Index out of range. Line 36. Jesus. I'm having real trouble today, guys. I apologize. Okay. There we go. So, even though this guy has no children, it does. And the reason is because of this. Doing this creates a reference to memory. And every time this is initialized, it is referring to the same reference in memory. So if you define a empty list in the constructor, it is always going to refer to the same list. I'm sorry, not in the constructor, in the default parameters. And this will, you'll be able to add to that number, to that list every time. And it will be one shared resource among the nodes. So the reason why we do this is to make sure that each node gets its own list of children. Okay. So this is a generic tree node. This is really the guts of it, this constructor. But as we're going to see coming up next, that really we want specific algorithms to work with specific types of trees. So that's going to be sort of your best practice going forward.